Hello everyone, welcome. Today we're going to talk about element number 22, titanium. Titanium is one of the most popular element names. So popular that marketers apply it to thousands of products whether they contain actual titanium or not. If you have a golf club with the word quote-unquote titanium prominently molded onto the metal of the club, you may want to think twice before concluding that it's actually made of titanium. Some are not. An easy test is to hold the club up against a grinding wheel. If you don't see the characteristic bright white sparks of genuine titanium, then you haven't damaged anything of value. So if you're trying to figure out whether something is made out of titanium, you can quickly figure it out by sparking it. Here we have a metal, probably iron or some other metal. It creates yellowish sparks. If you see white sparks, then you have titanium, and if you see yellowish sparks, then you have another metal. Titanium stands for strength, both the name after Titans, gods of Greek legend, and in fact, it's used in jet engines, tools, and rockets for its tremendous strength. It's also completely non-rusting and non-allergenic, so much that it's popular for use inside the body in the form of artificial hip joints, dental implants, and body jewelry, i.e. tongue studs, eyebrow rings, and other such items commonly found stuck in teenagers. Though titanium metal is expensive, its ore is actually quite abundant. The high cost comes from refining difficulty, not scarcity. Titanium dioxide is everywhere. It is the white in white paint, and in all other colors of paint, TiO2 is the opacity, the substance that prevents what's underneath from showing through. Even the hardcover edition of this eBooks paper contains titanium dioxide to keep print on one side from showing through to the other. From missiles to razors, titanium is a very popular superstar and must be a source of great envy to its neighbor, vanadium, which labors in obscurity even when helping create an alloy of much greater strength than titanium. If you're interested in learning about vanadium, the link is in the description below. So titanium dioxide, miracle coating. Titanium dioxide, more properly called titanium 4 oxide, is a very important material. Approximately 1.5 million tons of the substance is produced each year in the United States for use as a pigment in paper and paints and as a component of sunscreens. In recent years, however, scientists have found a new use for titanium dioxide. When surfaces are coated with titanium dioxide, they become resistant to dirt and bacteria. For example, the Pilkington Glass Company is now making glass coated with TiO2 that cleans itself. All the glass needs is sun and rain to keep itself clean. The self-cleaning action arises from two effects. First, the coating of TiO2 acts as a catalyst in the presence of ultraviolet light, UV light, to break down carbon-based pollutants to carbon dioxide and water. Second, because titanium dioxide reduces surface tension, rainwater quote-unquote sheets, instead of forming droplets on the glass, thereby washing away the grime on the surface of the glass. Although this self-cleaning glass is bad news for window washers, it can save millions of dollars in maintenance costs for owners of commercial buildings. Because titanium dioxide treated glass requires UV light for its action, it does not work well for interior surfaces, where UV light is present only in small amounts. Otherwise, you would get a sunburn indoors. However, a team of Japanese researchers has found that if the Ti2 coating is doped with nitrogen atoms, it will catalyze the breakdown of dirt in the presence of visible light as well as UV light. Studies also show that this N-doped TiO2 surface coating kills many types of bacteria in the presence of visible or ultraviolet light. This discovery could lead to products such as self-sterilizing bathroom tiles, counters, and toilets. In addition, because the TiO2 on the surface of the glass has such a strong attraction for water molecules, greatly lowering the surface tension, water does not bead up to form droplets. Just as this effect produces sheeting action on exterior glass, so it prevents interior windows and mirrors from quote-unquote fogging up. So no more of those car drawings as you drive on a rainy, cold day. Aww. Titanium dioxide, a cheap and plentiful material, may prove to be worth its weight in gold as a surface coating. So again, a quick review. The titanium dioxide acts as a catalyst in the presence of UV light. This breaks down carbon-based pollutants into CO2 and H2O. Like soap, TiO2 reduces surface tension and washes away materials when H2O is present. Aw man, I was gonna clean that. Titanium dioxide taking our jobs. Indoors it is. Can't forget about that nitrogen, that when combined with TiO2 will catalyze the breakdown of dirt in the presence of visible or UV light. Here's an image of titanium dioxide. Here's Ti and O. So the chemical impact, golfing with glass. You probably can guess what material traditionally was used to construct the quote-unquote woods used in golf. Modern technology has changed things. Like the bats used in college baseball, most quote-unquote woods are now made of metal. While bats are made of aluminum, golf club heads are often made of stainless steel or titanium. Metals and their alloys usually form crystals that contain highly ordered arrangements of atoms. However, a company called Liquid Metal Golf at Laguna Niguel, California, has begun producing golf clubs containing glass, metallic glass. The company has found that when molten mixtures of titanium, zirconium, nickel, beryllium, and copper are cooled, they solidify, forming a glass. Unlike crystalline materials that contain a regular array of atoms, glasses are amorphous. The atoms are randomly scattered throughout the solid. These golf clubs with metallic glass inserts have some unusual characteristics. Golfers who have tried the clubs say they combine hardness with a quote-unquote soft feel. Studies show that the glass transfers more of the energy of the golf swing to the ball with less impact to the golfer's hand with the regular metal woods. One of the fortunate properties of this 5-component metallic glass, invented in 1992 by William L. Johnson and Attican Peter at the California Institute of Technology, is that it can be cooled relatively slowly to form the glass. This allows manufacture of relatively large glass objects, such as inserts for golf club heads. Most mixtures of metals that form glasses must be cooled very rapidly to obtain the glass, which results in tiny particles of glass leading to powders. David S. Lee, head of manufacturing at Liquid Metal Golf, says that golf clubs were an obvious first application for this 5-component glass because golfers are used to paying high prices for golf clubs that employ new technology. So here's some of the chemicals commonly used in the manufacture of fireworks. We have potassium nitrate, potassium chlorate, potassium perchlorate, ammonium perchlorate, barium nitrate, barium chlorate, and strontium nitrate. And the fuels are aluminum, magnesium, titanium, which is the element that we're talking about in this video here, charcoal, sulfur, antimony sulfide, dextrin, red gum, and polyvinyl chloride. Titanium is widely distributed in the Earth's crust, 0.6% by mass. Because of its relatively low density and high strength, titanium is an excellent structural material, especially in jet engines, where light weight and stability at high temperatures are required. Nearly 5,000 kilograms of titanium alloys is used in each jet engine of a Boeing 747 jetliner. In addition, the resistance of titanium to chemical attack makes it a useful material for pipes, pumps, and reaction vessels in the chemical industry. So, assume you work for an oil company that owns a huge natural gas reservoir containing a mixture of methane and nitrogen gases. In fact, the gas mixture contains so much nitrogen that it's unusable as a fuel. Your job is to separate the nitrogen, N2, from the methane, CH4. How might you accomplish this task? You clearly need some sort of quote-unquote molecular filter that will stop the slightly larger methane molecules, which have a size of 430 picometers, and allow the nitrogen molecules, which have a size of 410 picometers, to pass through. To accomplish the separation of molecules so similar in size will require a very precise quote-unquote filter. The good news is that such a filter exists. Recent work by Stephen Kuznick and Valerie Bell at Hearth Corporation in New Jersey and Michael Tsipatsis at the University of Massachusetts has produced a quote-unquote molecular sieve in which the pore passage sizes can be adjusted precisely enough to separate N2 molecules from CH4 molecules. This material involved is a special hydrated titanosilicate which contains H2O, titanium, silicon, oxygen, and strontium compound patented by Hearth known as ETS or Hearth titanosilicate 4. When sodium ions are substituted for the strontium ions in ETS4 and the new material is carefully dehydrated, a uniform and controllable pore size reduction occurs. The researchers have shown that the material can be used to separate N2, which have a size of 410 picometers, from O2, which have a size of 390 picometers. They have also shown that it is possible to reduce the nitrogen content of natural gas from 18% to less than 5% with a 90% recovery of methane. So, molecular sieve framework of titanium, which is in blue, silicon, which is in green, and oxygen, which is in red, atoms contract on heating at room temperature. Titanium nitrate is the inorganic compound with the formula TiNO3 TiO4. It is a colorless, diamagnetic solid that sublimes readily. It is an unusual example of a volatile binary transition metal nitrate. 3 defined species called titanium nitrate are produced upon dissolution of titanium or its oxides in nitric acid. According to Wikipedia, its formula is TiNO3-4. Its density is 2.19 grams per centimeters cubed. And here is its ChemSpider ID, 8123716. So here we have titanium. This metal is as tough as steel, but much lighter. Titanium can be easily refined into pure metal from its ore. It is mixed with aluminum to make super strong alloys for aircraft bodies and engines. Its atomic mass is 47.867. Its state is a solid. Its discovery was in 1791 by William Gregor. The body of an Airbus A380 Super Jumbo contains about 84 tons or 77 metric tons of titanium. The mineral brokerite is a natural form of compound called titanium dioxide. Here's a laboratory sample of pure titanium. Here's red-brown crystals of brokerite, an ore of titanium. The mineral albite, which does not contain titanium, grows alongside brookite, which does contain titanium. So as mentioned in previous video, titanium gold alloys, watches and jewelry are made of titanium gold alloys that are stronger and harder than pure gold. Here we have the titanium atom combined with the gold atom. If you're interested in learning more about gold, the link is in the description below if you're interested. And here we have some information relative reducing abilities of the first row transition metals in aqueous solution: scandium, titanium, vanadium, manganese, chromium, zirconium, iron, cobalt, nickel, and copper. The most familiar compound of titanium is no doubt responsible for the white color of this paper, titanium dioxide. Titanium dioxide, or more correctly titanium 4 oxide, TiO2, is a highly opaque substance used as the white pigment in paper, paint, linoleum, plastics, synthetic fibers, white wall tires, and cosmetics, sunscreens for example. Approximately 700,000 tons is used annually in these and in other products. Titanium 4 oxide is widely dispersed in nature, but the main ores are rutile, which is impure titanium dioxide, and ilmenite, which is iron, titanium, and oxygen, which is essentially oxidized titanium and iron. Rutile is processed by treatment with chlorine to form volatile TiCl4, which is separated from the impurities and burned to form TiO2. And here's an overview of the reaction. Here we have titanium, chlorine, oxygen, titanium, oxygen, and chlorine. Titanium, which comes from rutile, is very strong and is used in aircraft, spacecraft, missiles, and ships. Rutile is a type of oxide. Oxides form when oxygen combines with metals. They include ores, minerals from which metals are extracted, and gems. So rutile forms when titanium and oxygen combine. So ilmenite is treated with sulfuric acid to form a soluble sulfate. Here's a formula of the reaction with sulfuric acid to form an iron 2+ ion, aqueous, and a sulfate ion, 2-, also aqueous, and water, which is liquid or aqueous. When this aqueous mixture is allowed to stand under vacuum, solid FeSO4 times 7H2O forms first and is removed. The mixture is then heated and the insoluble titanium 4 oxide hydrate TiO2H2O forms. The water of hydration is driven off by heating to form pure TiO2. TiO2H2OS with heat forms TiO2 solid and H2O as a gas. In its compounds, titanium is most often found in the +4 oxidation state, which means that it lost 4 electrons. Examples are TiO2 and TiCl4. The latter is a colorless liquid, BP 137 degrees Celsius, that fumes in moist air to produce TiO2. And here's the formula. TiCl4 in liquid to form 2H2O liquid and TiO2S and 4HCl in gaseous form. Titanium 3 compounds can be produced by reduction of the +4 state. In aqueous solution, titanium 3+ exists as the purple TiH2O6 3+ ion, which is slowly oxidized to titanium 4 by air. Titanium 2 is not stable in aqueous solution, but does exist in the solid state in compounds such as TiO and the dihalides of general formula TiX2. Vanadium is widely spread throughout the Earth's crust, 0.02% by mass. It is used mostly in alloys with other metals such as iron. 80% of vanadium is used in steel and titanium. Vanadium 5 oxide, V2O5, is used as an industrial catalyst in the production of materials such as sulfuric acid. Pure vanadium can be obtained from the electrolytic reduction of fused salts, such as VCl2, to produce a metal similar to titanium that is steel gray, hard, and corrosion resistant. Often, the pure element is not required for alloying. For example, ferrovanadium, produced by the reduction of a mixture of V2O5 and F2O3 with aluminum, is added to iron to form vanadium steel, a hard steel used for engine parts and axles. The principal oxidation state of vanadium is +5, found in compounds such as the orange V2O5 MP 650 degrees Celsius and the colorless VF5 MP at 19.5 degrees Celsius. One of the most interesting characteristics of the world of bicycling is the competition among various frame materials. Bicycle frames are now built from steel, aluminum, carbon fiber composites, and titanium, with each material having advantages and disadvantages. Steel is strong, economical, adaptable, and unfortunately, quote-unquote, rustable. Aluminum is light and stiff, but has relatively low fatigue limits, or resistance to repeated stresses. Carbon fiber composites have amazing strength to mass ratios and have shock and vibration dampening properties superior to any metal. However, they are very expensive. Titanium has a density approximately 43% less than that of steel, a yield strength when alloyed with metals such as aluminum and tin that is 30% greater than that of steel, an extraordinary resistance to fatigue, and a high resistance to corrosion. But it is expensive and difficult to work. Of all these materials, titanium gives the bicycle that fanatics seem to love the most. After their first ride on a bicycle with a titanium frame, most experienced cyclists find themselves shaking their heads and searching hard for the right words to describe the experience. Typically, the word quote-unquote magic is used a great deal in the ensuing description. The magic of titanium results from its combination of toughness, stretchability, and resilience. A bicycle that is built stiff to resist pedaling loads usually responds by giving a harsh, uncomfortable ride. A titanium bike is very stiff against high pedaling torques, but it seems to transmit much less road shocks than bikes made of competitive materials. Why titanium excels in dampening vibrations is not entirely clear. Despite titanium's significantly lower density than steel, shockwaves travel more slowly in titanium than in steel. Whatever the explanation for its shock-absorbing abilities, titanium provides three things that cyclists find crucial: lightweight, stiffness, and a smooth ride. Magic. Titanium is quite abundant in Earth's crust, ranking 9th of all the elements and 2nd among the transition elements. The metallurgy of titanium presents special challenges. Carbon, the reducing agent most commonly used to obtain metals from their oxide, cannot be used because it forms intractable interstitial carbides with titanium, which simply means that it can't be used to remove oxides from titanium, because it would simply form titanium carbides. These carbides are extraordinarily hard and have melting points close to 3000 degrees Celsius. However, if chlorine gas is used in conjunction with carbon to treat the ore, volatile titanium tetrachloride is formed, which can be distilled off and then reduced with magnesium or sodium at approximately 1000 degrees Celsius to form a titanium quote-unquote sponge. This sponge is then ground up, cleaned with aqua regia, a 1:3 ratio mixture of concentrated nitric acid and concentrated hydrochloric acid, its formula being HNO3 and HCl respectively, melted under a blanket of inert gas to prevent reaction with oxygen, and cast into ingots. Titanium, a lustrous silvery metal with a high melting point, 1667 degrees Celsius, crystallizes in a hexagonal closed pack structure. Because titanium tends to become quite brittle when trace impurities such as carbon, nitrogen, and oxygen are present, it must be fabricated with great care. Titanium's unusual ability to stretch makes it hard to machine. It tends to push away even from a very sharp cutting blade, giving a rather unpredictable final dimension. Also, because titanium is embrittled by reaction with oxygen, all welding operations must be carried under a shielding gas such as argon. However, just like this video, the bicycle that results is worth all the difficulties. One woman described a titanium bicycle as quote-unquote the one God rides on Sunday. Is a titanium bike better than a carbon bike? Titanium bikes are much more durable than carbon fiber. The reason is that titanium is a much less brittle material. During an impact, a titanium frame is less likely to crack, bend, or dent. Titanium frames are also resistant to corrosion, unlike steel. Titanium is as strong as steel, but much less dense. It is therefore important as an alloying agent with many metals including aluminum, molybdenum, and iron. These alloys are mainly used in aircraft, spacecraft, and missiles because of their low density and ability to withstand extremes of temperature. They are also used in golf clubs, laptops, bicycles, and crutches. Power plant condensers use titanium pipes because of their resistance to corrosion. Because titanium has excellent resistance to corrosion in seawater, it is used in desalination plants and to protect the hulls of ships, submarines, and other structures exposed to seawater. Is titanium good for submarines? An extremely light and durable metal, titanium brings several advantages over a standard steel hull construction. A titanium construction facilitates higher pressure tolerances, allowing a submarine to operate at significantly greater depths. Titanium metal connects well with bone, so it has found surgical applications such as in joint replacements, especially hip joints, and tooth implants. The largest use of titanium is in the form of titanium 4 oxide. It is extensively used as a pigment in house paint, artist paints, plastics, enamels, and paper. It is a bright white pigment with excellent covering power. It is also a good reflector of infrared radiation and so is used in solar observatories where heat causes poor visibility. Titanium 4 oxide is used in sunscreens because it prevents ultraviolet UV light from reaching the skin. Nanoparticles of titanium 4 oxide appear invisible when applied to the skin. Titanium is important as an alloying agent with most metals and some nonmetals. Some of these alloys have much higher tensile strengths than does titanium itself. Titanium has excellent corrosion resistance in many environments because of the formation of a passive oxide surface film. No noticeable corrosion of the metal occurs despite exposure to seawater for more than 3 years. Titanium resembles other transition metals such as iron and nickel in being hard and refractory. Basic refractories are used in areas where slags in atmosphere are basic. They are stable to alkaline materials but can react to acids. The main raw materials belong to the RO group, of which magnesia, MgO, is a common example. Other examples include dolomite and chrome magnesia. Its combination of high strength, low density, it is quite light in comparison to other metals of similar mechanical and thermal properties, and excellent corrosion resistance make it useful for many parts of an aircraft, spacecraft, missiles, and ships. It also is used in prosthetic devices because it does not react with fleshy tissue and bone as previously mentioned. Titanium has also been utilized as a deoxidizer in steel and as an alloying addition in many steels to reduce grain size, in stainless steel to reduce carbon content, in aluminum to refine grain size, and in copper to produce hardening. Although at room temperatures, titanium is resistant to tarnishing, at elevated temperatures, it reacts with oxygen in the air. This is no detriment to the properties of titanium during forging or fabrication of its alloys. The oxide scale is removed after fabrication. In the liquid state, however, titanium is very reactive and reduces all known refractories. The aerospace market is still the most important, with titanium products being used in both commercial and military aircraft. Gas turbines account for nearly half of annual titanium production. Titanium alloys are utilized principally in the fan and compressor sections at temperatures up to 600 degrees Celsius. Typical parts include inlet cases, compressor blades, discs, and hubs, as well as spacers and seals. The large high-bypass turbofan engines utilized on wide-body commercial airliners could not have been developed without strong, lightweight titanium alloys. These engines are greater than 25% by weight titanium. Titanium alloys are also utilized in airframes because of their high strength-to-weight ratio, good toughness, and corrosion resistance. The titanium content of airframes can range from as low as 2% to as high as 30% by weight. Typical commercial airframes are 4 to 8% titanium, while many military aircraft contain greater amounts. The metal is used in fasteners, landing gear supports, springs, fail-safe straps, and numerous internal bulkhead and wing support components. Titanium is resistant to all natural environments, including natural waste products, body fluids, and salt and brackish water, to most salt solutions including chlorides, bromides, iodides, and sulfides, and to most oxidizing acids, organic acids, and alkaline solutions. When strength is not a major consideration, commercially pure titanium is the material of choice because of its low cost, ease of fabrication, and good corrosion resistance. Alloys such as Ti 0.15 palladium, titanium 0.3 molybdenum, 0.8 nickel, and titanium 3 aluminum, 8 vanadium, 6 chromium, 4 molybdenum, and 4 zirconium can extend the usefulness of the metal to either higher temperatures or stronger concentrations of reducing acids and acidic salts. In more recent years, more high-strength alloys have been utilized for corrosion applications. For example, titanium, 6 aluminum, 4 vanadium, a versatile alloy that was developed in the 1950s for the aerospace industry, has become a very important material for medical prostheses such as hip joint replacements because of its high strength to weight ratio and immunity to body fluids, as previously mentioned. Titanium, 3 aluminum, 8 vanadium, 6 chromium, 4 molybdenum, and 7 zirconium, an even stronger alloy, has an excellent resistance to high-temperature sour gas, natural gas containing hydrogen sulfide, and is therefore used in energy extraction for downhole tubing and casing for instrumentation. Hydrogen sulfide is a chemical compound with the formula H2S. It is a colorless chalcogen hydrate gas and is poisonous, corrosive, and flammable, with trace amounts in ambient atmosphere having a characteristic foul odor of rotten eggs. Hydrogen sulfide, H2S, is a colorless gas with a strong odor of rotten eggs. Exposure to hydrogen sulfide may cause irritation to the eyes and respiratory system. It can also cause apnea, coma, convulsions, dizziness, headache, weakness, irritability, insomnia, stomach upset, and if liquid, frostbite. Several industrial processes have been improved as a result of the availability of titanium. After titanium was introduced as a replacement for stainless steel diffusion washers in the pulp and paper industry, the metal's excellent performance encouraged the design of new displacement bleaching systems using up to 35 tons of titanium components. Typical parts include diffusers, central shafts, scrapers, filtrate pumps, heat exchangers, packing boxes, and valves. In the early 1960s, it was discovered that coating titanium with a platinum group metal or metal oxide produced an anode, which is a negatively charged electrode, that was slow to corrode in electrolytic solutions. Coated titanium anodes soon replaced graphite anodes in the chlorine industry, resulting in lower costs and products of higher purity. Extensions of this technology are now being applied to electrogalvanizing and tin coating processes. Chemical process industries utilize titanium heat exchangers to eliminate corrosion problems caused by cooling waters containing chloride and sulfide, and several benefits can accrue from employing titanium on the process side of heat exchangers as well. Because the metal is resistant to corrosion, titanium vessels can be subjected to process liquids flowing at high rates, thereby eliminating the danger of biofouling. Biofouling, or biological fouling, is the accumulation of microorganisms, plant, algae, or small animals where it is not wanted on surfaces such as ships and submarine hulls, devices such as water inlets, pipework, grates, ponds, and rivers that cause degradation to the primary purpose of that item. According to Wikipedia, titanium helps against biofouling. In addition, titanium is the only metal known to be completely resistant to all forms of biofouling corrosion. These advantages, along with its light weight, make the metal desirable for heat exchangers in naval vessels and offshore oil platforms. Titanium is gaining greater recognition in consumption applications such as eyeglass frames, watches, sport equipment, jewelry, high-performance automobiles, and roofing. Other possible applications include valves for automobile engines, scrubbers for flue gas desulfurization, marine and offshore risers, joint and fitting, and nuclear waste storage and transportation casks. Titanium, chemical element, a silvery gray metal of group 4 of the periodic table. Titanium is a lightweight, high-strength, low-corrosion structural metal and is used in alloy form for parts in high-speed aircraft. A compound of titanium and oxygen was discovered in 1791 by the English chemist and mineralogist William Gregor, and independently rediscovered in 1795 and named by German chemist Martin Heinrich Klaproth. William Gregor was the British clergyman and mineralogist who discovered the elemental metal titanium, according to Wikipedia. Martin Heinrich Klaproth was a German chemist. He trained and worked for much of his life as an apothecary, moving in later life to the university. His shop became the second largest apothecary in Berlin, and the most productive artisanal chemical research center in Europe, according to Wikipedia. He discovered uranium, zirconium, cerium, tellurium, and beryllium. So again, titanium is used in high-speed aircraft. A supersonic aircraft is an aircraft capable of supersonic flight, which is an aircraft able to fly faster than the speed of sound, which we call Mach 1. So if something is flying Mach 2, they're flying 2 times faster than the speed of sound, and if they're flying Mach 3, they're flying 3 times faster than the speed of sound. If an object is flying faster than the speed of sound, they're literally moving through space faster than the sound that they're making through the air. So how did William Gregor discover titanium? The first titanium compound was identified by a Cornish vicar named William Gregor in 1791 when he extracted the impure oxide. He dissolved it in acid and got a colorless solution, but found that it could be reduced by zinc to make a purple solution. He was a transition metal chemist ahead of his time. The first titanium mineral, a black sand called Manuka Knight, was discovered in 1791 in Cornwall by the Reverend William Gregor. He analyzed it and deduced it was made up of the oxides of iron and an unknown metal, and reported it to the Royal Geological Society of Cornwall. In 1795, the German scientist Martin Heinrich Klaproth of Berlin investigated a red ore known as Schrol from Hungary. This is a form of rutile, TiO2, and Klaproth realized it was an oxide of a previously unknown element which he named titanium. When he was told of Gregor's discovery, he investigated Manuka Knight and confirmed it too contained titanium. It was not until 1910 that M.A. Hunter, working for General Electric in the USA, made pure titanium metal by heating titanium tetrachloride with sodium metal. The formula is seen here. Titanium tetrachloride is the inorganic compound with the formula TiCl4. It is an important intermediate in the production of titanium metal and the pigment titanium dioxide. TiCl4 is a volatile liquid, according to Wikipedia. So here's the unbalanced formula, and here's the balanced formula. It takes 4 moles of sodium to combine with 1 mole of titanium tetrachloride to create 4 moles of sodium chloride and 1 mole of titanium. So again, as previously mentioned, titanium dioxide, also known as titanium 4 oxide or titania, is the inorganic compound with the chemical formula TiO2. When used as a pigment, it is called titanium white, pigment white 6 or Cl77891. It is a white, water-insoluble solid, although mineral forms can appear black, according to Wikipedia. Its formula is TiO2. Titanium ore was first discovered in 1791 in Cornish beach sands by an English clergyman, William Gregor. The actual identification of the oxide was made a few years later by a German chemist, Martin H. Klaproth. Klaproth gave the metal constituent of this oxide the name titanium, after the Titans, the giants of Greek mythology. Pure metallic titanium was first produced in either 1906 or 1910 by M.A. Hunter at Rensselaer Polytechnic Institute, Troy, New York, US, in cooperation with the General Electric Company. The researchers believed titanium had a melting point of 6,000 degrees Celsius or 10,800 degrees Fahrenheit, and was therefore a candidate for incandescent lamp filaments. But when Hunter produced a metal with a melting point closer to 1,800 degrees Celsius or 3,300 degrees Fahrenheit, the effort was abandoned. Spoiler alert, they end up using tungsten instead. We'll talk about that in the tungsten video. Hunter did indicate that the metal had some ductility, and his method of producing it by reacting titanium tetrachloride, TiCl4, with sodium under vacuum. Nevertheless, Hunter did indicate that the metal had some ductility, and his method of producing it by reacting titanium tetrachloride, TiCl4, with sodium under vacuum was later commercialized and is now known as the Hunter process. Metal of significant ductility was produced in 1925 by the Dutch scientists A.E. van Arkel and J.H. de Boer, who dissociated titanium tetraiodide on a hot filament in an evacuated glass bulb. In 1932, William J. Kroll of Luxembourg produced significant quantities of ductile titanium by combining TiCl4 with calcium. Here's the unbalanced and balanced formula. By 1938, Kroll had produced 20 kilograms or 50 pounds of titanium and was convinced that it possessed excellent corrosion and strength properties. At the start of World War II, he fled Europe and continued his work in the United States at the Union Carbide Company and later at the U.S. Bureau of Mines. By this time, he had changed the reducing agent from calcium to magnesium metal. Kroll is now recognized as the father of the modern titanium industry, and the Kroll process is the basis for most current titanium production. The U.S. Air Force study conducted in 1946 concluded that titanium-based alloys were engineering materials of potentially great importance, since the emerging need for higher strength-to-weight ratios in jet aircraft structures and engines could not be satisfied efficiently by either steel, which is made out of iron and carbon, or aluminum. As a result, the Department of Defense provided production incentives to start the titanium industry in 1950. Similar industrial capacity was founded in Japan, the USSR, and the United Kingdom. After the impetus was provided by the aerospace industry, as usual, the ready availability of the metal gave rise to opportunities for new applications in other markets, such as chemical processing, medicine, power generation, and waste treatment. Titanium is the 9th most abundant element on Earth. It is almost always present in igneous rocks and the sediments derived from them. It occurs in the minerals ilmenite, rutilite, and sphene, and is present in titanites and many iron ores. A titanate or sphene is a calcium-titanium nesosilicate mineral consisting of calcium, titanium, silicon, and 5 atoms of oxygen. Trace impurities of iron and aluminum are typically present. Also commonly present are rare earth minerals including cerium and yttrium. Calcium may be partially replaced by thorium, according to Wikipedia. Here we have calcium, titanium, silicon, and oxygen. Titanium is produced commercially by reducing titanium 4 chloride with magnesium. Titanium 4 oxide is produced commercially by either the quote-unquote sulfate process or the quote-unquote chloride process, both of which use the mineral ilmenite as a starting material. Ilmenite is an iron oxide mineral of the oxide and hydroxide group with the structural formula FeTi2O3. The structure is similar to that of hematite, where the two F3+ in hematite are replaced by one F2+ and one Ti4+ in ilmenite. Titanium oxide is widely prized for its opaque quality in coatings, plastics, high-gloss paints, ceramics, industrial enamels, papers, and inks. The compound is non-toxic and is the most common white pigment in the world. Titanium carbide, TiCl, is used extensively for cutting tools because of its combination of wear resistance and high hardness. It is one of the hardest natural carbides. Titanium nitride, TiN, has an attractive yellow color that is used in jewelry and decorative glass coatings. The high hardness of this compound has also made it very attractive as a coating to extend the life of tools. The electronics industry uses titanium nitride in very large-scale integration microprocessors as gates and diffusion barriers. Titanium tetrachloride, the starting material for TiO2 pigments and titanium metal, serves the same function for many titanium compounds and is used as a catalyst as well. The titanium aluminide intermetallic compounds Ti3Al and TiAl have attractive engineering properties that make them potential replacements for nickel-based superalloys in aircraft engines at temperatures from 600 to 870 degrees Celsius or 1100 to 1600 degrees Fahrenheit. A major impediment to wider use is their low ductility, which means that it's very difficult to manufacture titanium into wires. Here's some more information on titanium. Titanium carbide, TiC, is an extremely hard refractory ceramic material, similar to tungsten carbide, which consists of WC. It has the appearance of black powder with the sodium chloride crystal structure, so it's similar to sodium chloride, NaCl, because it's in a cubic form. Titanium processing is the extraction of titanium from its ores and the preparation of titanium alloys or compounds for use in various products. This metal is as tough as steel, but much lighter. Titanium can be easily refined into pure metal from its ore. It is mixed with aluminum to make super strong alloys for aircraft bodies and engines. So in the aluminum video and the airplane video, I mentioned that airplanes are made of aluminum. Well, not just aluminum, also titanium, because it adds strength, rigidity, and structure to it. Element number 22. I am gleaming, extremely hard, and very resistant to any type of chemical attack. As a brilliant white dioxide compound, Me plus 2 oxygen atoms, I make excellent paint. My main use is for super hard metal alloys whose unrivaled combo of lightness and strength means they often get used in aircraft and spacecraft manufacturing. Its date of discovery was in 1791. Titanium's density is 4.507 grams per centimeters cubed. Its melting point is 1,668 degrees Celsius or 3,034 degrees Fahrenheit. Its boiling point is 3,287 degrees Celsius or 5,949 degrees Fahrenheit. Titanium chemical symbol Ti is a soft, ductile, silvery gray metal with a melting point of 1,675 degrees Celsius or 3,047 degrees Fahrenheit. Owing to the formation on its surface of an oxide film that is relatively inert chemically, like aluminum, it has excellent corrosion resistance in most natural environments. So here I crossed out the word aluminum for titanium because since it has similar properties, it also applies to the element titanium. So this can be read as how titanium corrodes. Titanium also reacts with oxygen in the air and forms a layer of titanium oxide. However, this form of corrosion does not crumble or erode like rust. The layer sticks to titanium, preventing further corrosion. A layer of titanium oxide forms a protective layer over titanium. Don't even need to rewrite the book, just replace the word aluminum for titanium. In addition, it is light in weight with a density of 4.51 grams per cubic centimeter, midway between aluminum and iron. Its combination of low density and high strength gives it the most efficient strength to weight ratio of common metals for temperatures up to 600 degrees Celsius or 1,100 degrees Fahrenheit. Titanium is very useful because it's very strong and very light. When something is strong as well as light, it can be utilized for flight. Because its atomic diameter is very similar to many common metals such as aluminum, iron, tin, and vanadium, titanium can be easily alloyed to improve its properties. Like iron, the metal can exist in two crystalline forms: hexagonal, close-packed, HCP, below 883 degrees Celsius or 1,621 degrees Fahrenheit, and body-centered cubic, BCC, at higher temperatures up to its melting point. This allotropic behavior and the capacity to alloy with many elements results in titanium alloys having a wide range of mechanical and corrosion-resistant properties. Although titanium ores are abundant, the high reactivity of the metal with oxygen, nitrogen, and hydrogen in the air at elevated temperatures necessitates complicated and therefore costly production and fabrication process. Although workable known reserves of rhyolite are diminishing, ilmenite deposits are abundant. Typical mining is by open pit. A suction bucket wheel on a floating dredge supplies a mineral-rich sand to a set of screens called trommels, which remove unwanted materials. Typically, the minerals are separated from waste material by gravity separation. Gravity separation is an industrial method of separating two components, either a suspension or dry granular mixture, where separating the components with gravity is sufficiently practical. The components of the mixture have different specific weight, according to Wikipedia. Gravity separation is done in a wet spiral concentrator. The resulting concentrates are separated by passing them through a complex series of electrostatic, magnetic, and gravity equipment. So here's a question. What are trommels used for? Trommels are frequently used in gravel processing to sort gravel of different sizes. A trommel is a rotating drum with a screen that allows fine material to fall through while retaining larger materials. Here's some more information. What is a wet spiral separator? Spiral separators of the wet type, also called spiral concentrators, are devices to separate solid components in a slurry, based upon a combination of the solid's particle density as well as the particle's hydrodynamic properties, e.g. drag, according to wikipedia.org. Here's some more information on ilmenite. Ilmenite is the most important ore of titanium and the main source of titanium dioxide, which is used in paints, printing inks, fabrics, plastics, paper, sunscreen, food, and cosmetics, according to Wikipedia. Ilmenite is an iron oxide mineral of the oxide and hydroxide group with structural formula FeTi2O3, as previously mentioned. The production of titanium metal accounts for only 5% of annual titanium mineral. The rest goes to the titanium pigment industry. Pigments are produced using either a sulfate process or a more environmentally acceptable carbon chlorination process that converts TiO2 into TiCl4, or titanium tetrachloride. The latter process also supplies the titanium tetrachloride, TiCl4, necessary for the production of titanium metal. Environmental and economic constraints dictate that the ore feedstocks converted by carbochlorination processes now in use contain greater than 90% TiO2. Only natural rutile meets the requirement, but ilmenite can be upgraded through combinations of pyrometallurgical and hydrometallurgical techniques to produce a synthetic rutile of 90 to 35% titanium dioxide, TiO2, which is essentially oxidized titanium. Rutile, leucoxene, synthetic rutile, and slag can be mixed to provide a feedstock of more than 90% Ti2 for the chlorination process. In the first step of this process, the oxide ores are treated with chlorine in a fluidized bed of petroleum coke. Oxygen combines with carbon, C, in the coke to produce carbon monoxide, CO, and carbon dioxide, CO2, while the titanium and chlorine react to form a gaseous TiCl4 as in the following reaction. Here we see titanium dioxide, here we see carbon. This represents variable quantities whose ratio depends on the reaction temperature, which varies between 850 and 1000 degrees Celsius or 1550 and 1800 degrees Fahrenheit. The raw TiCl4 is cleaned of fine particles of entrained coke and titanium ore, and then is liquefied and passed through a distillation column to remove volatile impurities of both high and low boiling points. Vanadium oxychloride, an impurity with a boiling point similar to a TiCl4, is stripped from the product stream by reaction with mineral oil. The TiCl4 is then redistilled to remove other impurities in a reflux distillation column. This produces TiCl4 of a purity exceeding 99.9%. Since any contaminants in the TiCl4 would later be reduced along with the titanium metal, high-quality TiCl4 must be produced to achieve high-quality metal. Vanadium oxytrichloride is the inorganic compound with the formula VOCl3. This yellow distillable liquid hydrolyzes readily in air. It is an oxidizing agent. It is used as a reagent in organic synthesis. Samples often appear red or orange owing to an impurity of vanadium tetrachloride, according to Wikipedia. In the production of titanium pigments, the TiCl4 would be reoxidized to TiO2, but in the production of titanium metal, it is reduced with either sodium Na in the Hunter process or with magnesium Mg in the Kroll process. Here we see both of the balance formulas for titanium tetrachloride reacting with two different metals, sodium and magnesium. We talked about magnesium in a previous video. If you're interested in learning about that element, we'll talk about sodium in a future video. When titanium tetrachloride reacts with sodium, it produces titanium and 4 moles of sodium chloride. When titanium tetrachloride reacts with magnesium, it creates magnesium dichloride. So correction, the balance formula is correct. It's just 2 chlorine atoms per 1 atom of magnesium. These reactions take place in large sealed vessels at approximately 800 to 1000 degrees Celsius or 1450 to 1800 degrees Fahrenheit in an inert argon atmosphere to avoid contamination of the final product by air or moisture. Both processes produce titanium in the form of a highly porous material called sponge, with the salts NaCl or MgCl2 entrapped in the pores. The sponge is crushed and the metal and salts are separated by either a dilute acid leach or by high temperature vacuum distillation. The salts are recycled through electrolytic cells to produce sodium or magnesium for reuse in metal reduction and chlorine for use in chlorination of the ore. A different process that offers hope for an improved and simplified method of producing titanium metal is the direct electrowinning of titanium from TiCl4 in fused chloride salt baths. In this case, titanium sponge collects on a steel cathode and chlorine gas is given off at the carbon anode. The required use in this process of high melting point salts combined with the need for maintaining an inert environment present major technical and economic hurdles that have to be overcome in order to achieve commercial status. The conversion of purified titanium sponge to a form useful for structural purposes involves several steps. Consolidation into titanium ingot is performed in a vacuum or argon environment by the consumable electrode arc melting process. Sponge, alloying elements, and in some cases, recycled scrap are first mechanically compacted and then welded into a long cylindrical electrode. The electrode is melted vertically onto a water-cooled copper crucible by passing an electric current through it. To ensure uniform distribution of alloying elements, this primary ingot is remelted at least once in a similar manner. Ingots weigh between 4 and 10 tons and are up to 1,050 millimeters, or 42 inches in diameter. Cold hearth melting is an alternative consolidation process that is conducted inside an argon or vacuum chamber containing a water-cooled horizontal copper crucible. Heating is accomplished by multiple electron beam or by argon-helium plasma torches. The molten metal flows in a horizontal path over the lip of the hearth into a suitably shaped, water-cooled copper mold. The cold hearth process is well suited to separating high-density contaminants which settle to the bottom of the hearth. For this reason, it is used primarily to recycle titanium scrap, which can contain carbide tool bits left over from machining operations. Consolidated ingots are processed into mill products such as bar, billet, wire, tubing, plate, and sheet by traditional sheet facilities. The atoms of pure titanium align in the solid state in either a hexagonal close-packed crystalline structure called the alpha phase or body-centered cubic structure called the beta phase. In the pure metal, transformation from the alpha to beta phase occurs upon heating above 883 degrees Celsius, but most alloying elements either stabilize the alpha phase to higher temperatures or stabilize the beta phase to lower temperatures. Aluminum and oxygen are typical alpha stabilizing elements, and typical beta stabilizing elements are vanadium, iron, molybdenum, nickel, palladium, niobium, silicon, and chromium. A few other alloying elements, such as tin, Sn, and zirconium, Zr, have little effect on phase stabilization. The most important alloying element is aluminum, which, in concentrations up to 8% by weight of the alloy, can be added as a strengthener without impairing ductility. So finally, the biological role of titanium. Titanium has no known biological role. It is non-toxic, but fine titanium dioxide dust is a suspected carcinogen, so don't breathe that in. So that was titanium, element number 22, explained in 60 minutes or less. If you like this video, make sure to like, comment, subscribe. As always, thank you everyone for watching. The previous video was on cupernicium. The next element will be on platinum, explained in X minutes or less. Have a great one.